Let's now move on from GANs to another kind of deep generative models called Variational Autoencoders, popularly known as VAEs. Before we talk about variational autoencoders, let's briefly recall autoencoders, which we covered last week. Autoencoders are neural networks that are used for unsupervised learning, where the network attempts to reconstruct the input itself as the output. Autoencoders have an architecture such as this, where the input is compressed into a bottleneck layer where a certain representation of the input is available, which is also called a latent code, which is then used through a decoder to reconstruct the output, which we'd ideally like to resemble the input itself. The question we'd like to ask in the context of this week's topic is, how can we use such an approach to automatically generate images? Remember that we said when we spoke about autoencoders that once you train an autoencoder, we generally discard the decoder, and given an input, we use the encoder alone to get a low-dimensional representation of your data. Let's try to see now if we can reverse this idea, and at the end of training, can we discard the encoder instead of the decoder, and using some vector as code, if we can generate images close to the training data distribution. As you can see, the goal is close to what GANs were trying to achieve, but achieved with a different perspective. The idea of variational autoencoders was introduced around the same time by two groups of researchers, Kingma and Welling, in a paper known as Autoencoding Variational VAEs, published in ICLR of 2014. Also by Rezend, Muhammad and Wiestra, called Stochastic Backpropagation and Variational Inference in Deep Latent Gaussian Models, which was published in ICML of 2014. Let's try to understand variational autoencoders now. At the crux of VAEs is about learning what is known as a latent variable model. In a latent variable model, our objective is to learn a mapping from some latent random variable z to a possibly complex distribution on x, which we assume is the training real-world distribution that we'd like to generate data similar to. Mathematically speaking, you would then write p of x is equal to the integral of the joint distribution p of xz dz, where p of xz is equal to p of x given z into p of z. And we assume here is that the prior or the marginal distribution on z, the latent variable, is something simple. And how would you get p of x given z? P of x given z, we assume, is some function of an input vector z. So that would be the simple mathematical construction here. The question we are asking is, can we somehow learn given training data, assuming here it's unsupervised learning, only x, can we learn to decouple the true explanatory factors or the latent variables underlying the data distribution, which is perhaps generating the data? For example, in face images, you may want to assume that there is a latent random variable called identity, a latent random variable called expression. So if we say a person A is happy, you should be able to generate a face image of person A in a happy mood. So in this case, identity and expression would be latent variables, and those latent variables may assume different values. Identity may assume values of different people like A, B, C, and expression may assume different values like happy, sad, angry, so on and so forth. And the combination results in generation of specific kind of images. So we are talking about a latent set of variables, in this case represented as Z1, Z2, and a function G that takes us from this latent space to the original data space. How do we learn such a function G that takes us from Z to X? We're going to assume that we're going to use a neural network to learn such a function that takes us from Z to X. So this conditional distribution here. So given a vector Z, we ideally should be able to use a neural network to give us a vector X. The question now remains, where does Z come from? Computing the posterior P of Z given X is intractable because we don't know what Z's look like. That's not available to us. Unfortunately, we need that to be able to train the G of Z model. Without values of Z, we cannot train the G of Z model also. So how do we get around this problem? So as you can see so far, variational autoencoders offer a Bayesian spin on an autoencoder. So if we assume that our data is generated using this generative process, where Z are a set of latent random variables, which we assume belong to a certain prior distribution, we sample from a true conditional distribution, which results in X, which is the training data distribution that we see. The intuition here is X could be an image which is generated from some latent attributes such as a class label, an orientation, attributes, so on and so forth. So we could say that the class label is a person's face, the orientation is in which direction he or she is looking, attributes could be the color of the face, the color of the eyes, the color of the hair, so on and so forth. And the problem now for us is, without knowing what these Z's are, we need to estimate the parameters of this conditional distribution P of X given Z. The theta parameters is something that we'd like to estimate without having access to Z. How do we do this is the core idea of VAEs. To start this process, let's assume now that there is a prior distribution on the random variable Z, which for convenience we're going to assume is a unit Gaussian. And the moment you have Z, you can now construct a neural network, which we call the decoder network, with certain parameters theta, which are the weights of those layers in the decoder network. And the decoder outputs a set of means and variances, which can then be used to sample and get data similar to X. So the conditional distribution P theta of X given Z here is assumed to be diagonal Gaussian. That's for simplicity. One could assume a multivariate Gaussian with a certain covariance matrix, but the procedure gets a bit complex and we're going to keep it simple as a diagonal Gaussian whose means and variances are predicted by the decoder network. Each dimension of that multivariate Gaussian, the mean and the variance is predicted. Now from Bayes' rule, we know that P theta of Z given X, which is our posterior, is given by P theta of X given Z into P theta of Z by P theta of X. Now if we observe the terms on the right hand side, P theta of X given Z, we just talked about how you can obtain it. Assume that your Z's are a unit Gaussian and learn a decoder network which can give you the output X. So that gives you P theta of X given Z. What about P theta of Z? We just said we're going to assume that to be a Gaussian. So that's an assumption. What about the denominator, p theta of x? Unfortunately, that is an intractable integral. To be able to find out what distribution and what parameterization of that distribution x comes from is something we don't know at this time. So what do we do to get around this? We are now going to assume that there is some other distribution q phi of z given x, which we will now call as an approximate posterior. So this is obtained using an encoder network. What does the encoder network do? It takes in your training data distribution. So that's where your neural network takes in all the inputs from your training data. It has a set of layers parameterized by some weights which we denote as phi, and it outputs again set of means and variances of a multivariate Gaussian, of a multivariate diagonal Gaussian distribution. That is given by the approximate posterior q phi z given x. So if we put all these pieces together, we now have the encoder below and the decoder on top. The encoder takes x and gives out a set of means and variances for this approximate posterior distribution q phi of z given x. And once you have that distribution, you can sample a z from that distribution, and that sample z is given as input to your decoder network, and the decoder network outputs a set of means and variances which corresponds to p theta of x given z. And given these means and variances, you can sample from p theta of x given z to get your output images or reconstructions. We assume here that both q sub phi and p sub theta are multivariate Gaussians with a certain mean and a diagonal covariance. So each dimension is independent. So how do we train such a network? Let's try to understand that. We'd ideally like to train the decoder network just like the normal autoencoder. So because it's going to give us an output x, we'd ideally like to use something like a reconstruction loss, something like a mean squared loss, to ensure that this reconstruction here is as close as possible to x itself. That should definitely be one term of our loss function. What else do we need to do? We also want to ensure that this approximate posterior q phi of z given x should be close to the prior of z that we assumed. We assumed for the decoder network that z comes from a unit Gaussian prior. So we'd ideally like q phi of z given x to be close to the distribution p theta of z, which in our case we assume to be a Gaussian with mean 0 and identity matrix as its covariance matrix. Let's try to put these together and get the formal loss function to train such a variational autoencoder. Remember, the goal here is to do a maximum likelihood estimation. We have a training data set given by xi's, and we ideally like to learn the parameters theta, which are the parameters of your decoder, in such a way that you maximize the likelihood of that distribution generating your training data points. That's your maximum likelihood estimation for your data set. We're going to convert that to a log likelihood maximum log likelihood estimation, where the product gets converted to sum, and then you have log of p theta, which makes things a bit simpler mathematically. Now p theta of x, which is this internal term here, can be given by integral p theta of x z dz by definition, and this can be expanded as p theta of x given z into p theta of z dz, unfortunately, we are once again left with an intractable integral in this particular case. So let's try to see how to solve this maximum likelihood estimation problem. We're going to solve it with a twist. So let's rewrite the maximum log likelihood estimation problem. We have the log likelihood, log of p theta, which can be given by expectation over z vectors sampled from the approximate posterior of log of p theta of x. So if we sample z vectors from your approximate posterior and give as input to the decoder, the likelihood of generating samples similar to the training distribution must be high. Okay, that's what this first sentence means. Now, log of p theta of x can be written using Bayes' theorem as log of p theta of x can be written as p theta of x given z into p theta of z by p theta of z given x. That's just the Bayes' theorem written in a different way. And to this particular expression, we're going to multiply and divide the approximate posterior. Okay. It's just a simple multiplication and division by a constant. Now, once we have this expression equivalent to the maximum likelihood estimation setting for this problem, we can group terms differently to write this in a different manner. So the first term here, we can have log p theta of x given z stays the same way, and we write that as this first term here, expectation over z, log of p theta of x given z. Then you have another term here, q phi of z given x and p theta. Ideally, you would be able to write that as plus expectation over z log of p theta of z by q phi of z given x. Now, instead of adding it, we're going to subtract it and write it this way. So we have a minus expectation over z log q phi z given x divided by p theta of z. Okay, it's just the reciprocal with a sign change in the beginning. And then the remaining terms are these two terms here, p theta of z given x in the denominator and q phi in the numerator, which is what the third term gives us. That's what the third term gives us. So it's just grouping terms and writing it differently. Now, if you observe the second and third terms here, you would notice that the second term is the KL divergence between q phi of z given x, the approximate posterior, and the prior on z. And the third term is the KL divergence between the true posterior p theta of z given x and the approximate posterior q phi of z given x. That's what is written here below. We're going to write the second term as a certain KL divergence and the third term as a certain KL divergence. Now, if you observe here, KL divergence is a non-negative quantity. So the third quantity here will be greater than or equal to 0. And because this is a log likelihood estimation problem, we ideally like to maximize this quantity. So to maximize this quantity comprised of these three terms, where the third term is greater than or equal to 0, can be achieved by maximizing the first two terms by itself. So what we are saying now is we have a lower bound which is given by these first two terms. Remember, the third term is non-negative and is added to that. So this entire log likelihood will be lower bounded by these first two terms. So if we'd like to maximize the log likelihood, we can maximize this lower bound. This lower bound is also known as evidence lower bound or elbow. It's read out as elbow and that's why it's written like this, but it's actually ELBO, evidence lower bound. It's also known as the variational lower bound. And this entire procedure of optimization is known as a method called variational inference, where we introduce a variational distribution. In this case, the variational distribution for us is the approximate posterior Q5, and using that we try to learn the parameterizations of a distribution. So our goal now is to find theta star and phi star which maximize this evidence lower bound. That's what we'd ideally like to do. So let's put this together. We now are saying that we've introduced an inference model Q phi of z given x, the approximate posterior, that tries to approximate the original posterior by optimizing the variational lower bound that we saw. Remember, these two terms here are exactly what we had as the two terms here. Expectation over z log p theta of x given z minus the KL divergence between approximate posterior and prior on z, which is writing the same thing here. And we parameterize Q phi of z given x using our encoder network. So we now have an encoder and a decoder network. Let's see them individually before we put them together in this context. So given training data x, we provide that as input to an encoder. The encoder outputs means and variances of an approximate posterior distribution, which we'd like to have it as close to the prior on z. Then we sample from z and use the decoder to be able to generate x, which we'd like to have as close to the training data distribution. So how are we going to train this? If you look at the loss by itself, this is the overall loss. In this case, we're going to maximize, so not perhaps a loss, just the objective function. But there is one problem in this training procedure. If you noticed, what we said was we give the input distribution to the encoder. The encoder gives out a parameterization of the approximate posterior. Then we sample from a prior, which is then given to the decoder, and then you get your final output. Which means we now have an encoder-decoder model, an autoencoder, where in the middle step or the bottleneck layer step, we are going to sample a vector rather than forward propagate a vector. Why is this a problem? That sample may not be deterministic, and we would not know how to pass the gradients through that bottleneck layer to the encoder. That is a challenge. What do? We ideally somehow have to ensure that that sample that we get becomes independent of the encoder output. Because if it becomes independent of the encoder output, you can simply backpropagate your gradients through your decoder and encoder and assume that the randomness is coming from some external quantity. How do we separate the randomness from the encoder output? This is done using a trick known as the reparameterization trick, and this was one of the main contributions of the effort in the method called variational autoencoder. A simple trick, but that solves the problem in backpropagating through this network. So remember that we are going to sample z from, say, some approximate posterior distribution, which is given by a Gaussian distribution with mean at a certain mu z of x, with variances or standard deviations given by sigma z of x. Now, a sample that's drawn from such a distribution can be rewritten slightly differently. We can parameterize that sample z as z is equal to, you instead randomly sample a vector from a unit standard normal distribution, multiply it by the standard deviation learnt by the encoder network, add the mean learned by the encoder network, and now this becomes a sample. How did this get around the real problem? Remember, while in the earlier steps so far, you could now consider this to be something like this. So you have a set of layers in a neural network. So the earlier version of the variational autoencoder, one of the layers became stochastic, where you had to sample a vector and it was not a vector forward propagated through a neural network as we have seen so far. So because that was a sample, we would not have known how to backpropagate through that layer to the earlier layers, in our case the encoder. So the reparameterization trick suggests that let's fix that layer as output of a previous layer and instead bring in the stochasticity from a different variable from the outside and not that layer's output itself. If you see here now, that new sample is given by mu of z, which are outputs of the encoder, sigma of z, which are the outputs of the encoder also, into epsilon, which you could almost consider now like a bias vector which is coming from noise. It doesn't really affect backpropagation into earlier layers. It's just an external input given in that particular layer, and now you can backpropagate through the entire network using gradient descent the way we have seen it before. So you now have, given x in the encoder, you generate mu's and sigmas, then you sample z using the reparameterization trick, go through the decoder and generate mu's and sigmas at the output, from which you can sample and get any generations. So with the reparameterization trick, the entire variational autoencoder becomes backpropable, and you can use gradient descent and backpropagation to update the weights in the VAE and train the network. So as before, the objective function here is given by minus KL divergence of Q phi and P theta plus expectation of log P theta of x given z. Now log P theta of x given z turns out to be a simple reconstruction loss. We'd like this to be close to your training distribution, so you can use even a mean square error to maximize this likelihood, the second term. What about this first term? How can we, is that differentiable? How can we get the gradient for it for doing backpropagation? The key there is that we have assumed Q phi to be a Gaussian with certain means and variances which the encoder provides. We also assumed P theta of z to be a unit Gaussian. And the KL divergence between Gaussians is a well-defined formula which is differentiable. So that is what helps us ensure that we can compute the gradients and backpropagate and train this network end to end. So that completes our discussion of how VAEs are learned. To summarize and differentiate from autoencoders, traditional autoencoders are learned by reconstructing input, and they are often used to learn features, the low dimensional representations, which could then be used to train another neural network or an SVM or to train in any other supervised models. On the other hand, variational autoencoders conceptually are a marriage between Bayesian learning and deep learning, and after training a variational autoencoder, you could discard the encoder, just sample from your prior P theta of z, a unit Gaussian, and now your decoder has learned to generate images, taking a unit Gaussian as input to generate images that look close to your input data distribution. That's what allows VAE to become a generative model. What can VAEs do? Here are a couple of examples where a VAE was trained on the MNIST dataset and the Frey-Face dataset. You can see here that in the MNIST dataset, when the latent variables, which are the Z's in your VAE, are modified by small values. Remember, we'll be sampling some vectors. You can see that the generated images, that is the output of the decoder, gradually varies as the Z value is varied. That shows us that the variational autoencoder has indeed learned latent variable values that are capable of generating data smoothly on the manifold on which it lies. Similarly, just like how we saw for GANs, on the Frey-Phase dataset, you can learn latent variables such as expression and poses, which as you change the values of those corresponding latent random variables, you end up getting generations of face images with different poses and different expressions. What else can VAEs be used for? They have plenty of applications. We will see some of these next week in detail. But here are a few examples: image and video generation, super resolution, forecasting from static images, image in painting, many more, and we'll see some of them next week. VAEs have also been extended in numerous ways over the last few years. While we may not have the scope to cover all of these in this course, here are a few pointers if you'd like to know more. The original authors extended VAEs to get a semi-supervised variant where you can use labeled and unlabeled data to learn the VAE. Another popular extension, rather a powerful extension, was conditional VAE, where you could generate given a particular class label, for instance. So in the example that we've seen so far, in the construction that we've seen so far, we considered it to be an unsupervised learning problem and just thought only data was given and we were generating more data. You could modify that to assume that labeled data was given to us, and at inference, if you give a certain class label, the VAE would generate data points belonging to that class label. Those issues are discussed in conditional VAE. There's another variant known as importance weighted VAE, which weights the latent random variables differently to get more powerful generations. Then there's a denoising VAE, which you could consider as an extension of the denoising autoencoder to a VAE setting. Then VAEs have also been used for graphics. A popular network is called the inverse graphics network, which uses a VAE-like strategy to learn latent variables that can give you control in generating various kinds of objects, 3D objects, and so on and so forth. You could control the light angle, the rotation, the kind of object, so on and so forth, using an inverse graphics network, which effectively uses a VAE strategy. And finally, another kind of a network called adversarial autoencoders, which brings together GANs and VAEs, which is going to be a topic that we discuss in the immediately next lecture. Your homework for this time is to go through this tutorial on variational autoencoder, as well as go through this VAE example in PyTorch. If you're interested, it may also be worthwhile going through the original paper on variational autoencoders. And here are a couple of questions for you to think about. Why does the encoder of a VAE map to a vector of means and a vector of standard deviations? Why does the encoder not map to a vector of means and a covariance matrix? Okay, this is the encoder, remember, that gets you the approximate posterior. A similar question, what about the decoder? If we assumed a mean square error for the reconstruction loss, the second term in your objective for VAE, remember, can use mean square to get a reconstruction loss. What is the covariance of the P of x given z Gaussian distribution? What do you think it will look like? Think about it and we'll discuss soon.